Hello, I'm here to talk about my mega favorite number. What's a mega favorite number? Well, on YouTube right now, everyone's talking about their favorite number that's over 1 million. It's pretty good fun. If you think you might have a favorite number that's over 1 million, you should join in. So what is my mega fave number? It's 44,220,464. But what the heck is this number? Where did it come from? So, in order to tell you that, first I have to talk about chorded keyboards. So, assuming you know nothing about a chorded keyboard, it's like a regular keyboard in that it can, type things into your computer. But you might notice the distinct lack of very many keys. So the word chorded in chorded keyboard kind of comes from, in music, you play a single key, that's just one tone. But if you play multiple tones at the same time, that's a chord. And so likewise, with a chorded keyboard, it's not just one key represents one letter. You can press two different keys at the same time, and you get a different letter than if you pressed each of the individual keys. This is my chorded keyboard that I built based on the Asetniop project, which quite interesting, put together by Zach Dennis. So there's tons of stuff to read and play with online with that. I'll put some links in the comments. So when I first programmed this chorded keyboard, I just had the naive impression of once a key is pressed down, then start recording any other keys that get pressed down. And once all of the keys are released, then look at any keys that were pressed down, and that's what the chord is. But as it turns out, typing on a keyboard like that, with a regular keyboard, you can press down the T key, and then you can press down the H key before you finish releasing the T key, and it gives this kind of flow to your typing. But with a chorded keyboard that you have to release all of the keys before pressing the next keys, is this very kind of not so good. So the next thing I put in was a mode to look at how long each key is pressed for and compare it to how long each of the other keys or chords were pressed for. And then use that to determine which chords are meant to have been pressed and which chords are meant to have been ignored. So I put in an interactive demo mode to sort of show you how this works. And so I'll do ERE, I find is a very good example because it's pressing down this key for an E, then pressing down both of the keys together for an R, and then releasing for an E again. So like this. Now in this graph, you can see there's the E was pressed down, as you saw, right here, that's the length of time. Then the R was pressed down for a length of time, and then the E was pressed down for a length of time. Which is pretty cool. Obviously, it's a lot faster to type like that than to type. The same thing goes for chords that are unrelated to one another. If you don't finish releasing a chord before pressing the next chord, like in T and an H. So you see down here we got a TH, but what the keyboard actually saw was the chord for T pressed for this length of time, then the chord for B pressed for a very small amount of time, and then the chord for H pressed for the longest amount of time, and then a very, very small amount of time the chord for N was pressed before all of the chords were released, and it sent through its decision. I wanted a T and an H. So that was my sort of second development after just having regular chords that you release. But of course, I got daydreaming about other ways, other extensions. So one that I was thinking is not that you're pressing down a specific chord, but that you're pressing down chords in a kind of sequence. So you might be pressing this key and then this key, or pressing both of the keys at the same time, or pressing this key and then this key. And so I kind of got thinking of a chord not as a, combination of keys, but as a sequence of keys. But of course, if you start extending this out past just 2 keys pressed down, then it becomes very sort of cumbersome. It gives you a very, very large combination of patterns that you can put in, but it becomes no longer like a feeling of tap-tap, but a feeling of trying to remember individual keys that is the next one to press or release. So then I thought, if you're having to take the time to remember the keys to press and release, then it's just as good to try and remember a chord to press in the sequence and release. So that's how I came to the idea that the most reasonable extension to this system is to have chord sequences. Also modes would be good, but that's out of the scope of what I'm talking about today. So then my question, very topical, was, can I count how many possible sequences I can press with a given amount of key presses? And that's what led me to doing a bunch of math, blah blah blah, mega favorite number. So how do I think of a chord sequence in order to try and quantify exactly how many chord sequences there are? So basically, there are given states of amount of keys or chords that are pressed, and then there are transitions from one chord being pressed to another chord being pressed to another chord being pressed. And so I can quantify the amount of possible chord sequences for any given amount of transitions. It turns out that the exact chord doesn't really matter. What matters is how many keys are pressed down for that chord. Because in the example of like 3 keys, if you press this one down, then if you're going to press down another key, you have 2 options. If you press down this key, then to press down another key, you have 2 options. And to press down this key, you then have 2 options. So really you only need to know how many possible ways there are to transition from having an amount of keys pressed to another amount of keys pressed on a keyboard with a given number of keys. So I first started thinking about this just drawing transition diagrams. Here's a keyboard that has 2 keys on it, so 0 keys are pressed, 1 key is pressed, all 2 keys are pressed. So for the initial state, there's no possible ways of having pressed 1 key, no possible ways of having pressed 2 keys, and there's one possible way of having pressed no keys, because it's the starting state of not having pressed any keys yet. So then I made up the kind of key transition matrix of going from 0 keys to any number of other keys. So from 0 to 0, there's no transition that gets you from 0 to 0 because you're already not pressing any keys. However, to press one key down, there's two possible transitions. Press one key or press the other key. And then to press two keys, there's only one possible transition, pressing them both. Then if you have one key pressed down, then there's only one way to get back to 0 keys, releasing that key that you pressed. There's no way to get to one key pressed, because if you press the other key, now you have two keys. If you release that key, now you have no keys. So there's no way to transition from the amount of keys you have to the same amount. And that follows through for any amount of keys. No matter what, you can't transition from an amount of keys to pressing the same amount of keys, because you haven't made any state transition. So then finally, to get from pressing down one key to pressing down two keys, there's only one way to do it, pressing the other key. And finally, for having two keys pressed down, you can release both of them. That's one transition, getting back to 0 keys pressed. Or you can release either of the two keys, which is two transitions. So then for each of the transitions in a sequence, you just multiply this matrix by the different amount of ways that were already there to get to the previous transition. So the first one, you could push down either one of the two keys, or push down both of the two keys. And that gets you to 0 ways of having made one transition, 2 ways of having pressed one key, and 1 way of having pressed two keys. Then if you multiply the now, or actually, this almost caught me. You don't multiply having pressed 0 keys, because if you ever get to the state of having pressed no keys, you've ended the sequence, essentially sending through the chord to the computer. So you have to make sure, after the first transition, to no longer include 0 keys back into the sequence. But anyways, so having one key pressed down in one of 2 possible ways, you can then release it, which gives you 2 sequences that end at no keys pressed. 1 sequence, 2 sequence. Or you can press the other one, which gives you another 2 sequences. 1, 2. And those, of course, end with 2 keys pressed. Then, finally, for having pressed both keys, you can release both keys. That's 1 sequence. Or you can release either one of the keys. That's 1 sequence, 2 sequences. And so carrying on in this way, you can get the number of sequences possible to end at the 0 state after 1, 2 transitions, or 3 transitions, or 4 transitions, or so on and so forth. So putting that into a kind of formal math notation, apparently this transition is described by the binomial coefficient formula, which is n keys, n total keys, choosing k keys from those n possible keys. And it's calculated out with the formula n factorial over k factorial multiplied by n minus k factorial, which I sort of reason is the possible permutations of all possible keys divided by the possible permutations of the selected keys and multiplied by the possible permutations of unselected keys. What does that mean? I don't really know. I find the binomial coefficient formula very interesting and kind of enigmatic. but I trust that it does give you the number of combinations of k keys selected from n elements. So using that to calculate the different transitions in our transition matrix, we have the number of ways with k keys on your keyboard to go from B keys pressed before to A keys pressed after is this piecewise function, where we have if B is greater than A, that is, we had more keys pressed down and we released some of them, is a selection out of the number of keys that were pressed down. So, you know, if you had 4 keys on your keyboard and you have 3 of them pressed down and you're releasing keys, it doesn't matter that you have one already released. You can't release it anymore. And then you select from that the number of keys you pressed before, subtracting the number of keys you have pressed after gives you the number of keys that you released. So then if B is equal to A, as we've already seen, there's no transition. So it's 0 possible ways. And finally, if B is less than A, you had less keys pressed, and you pressed some of them, then that's, you know, pressing, selecting from K minus the already pressed keys. You can't, as before, press a key that's already pressed. And we select the number of keys pressed after, subtracting the number of keys pressed before, that is to say, the number of keys that were pressed during this transition. And so finally, the number of chord sequences after T transitions ending at A amount of keys pressed. Notably, this will be 0 a lot of the time because what we care about is the number of ways to complete a sequence and return to pressing no keys. But anyways, that's the sum of all of the keys before, from having no keys pressed, though actually no keys pressed is discounted after the first transition, all the way through having all of the keys pressed, where we multiply the number of ways of that previous state, the state at transitions -1, by the ways of having gotten to this, the state after that transition from the state before, as per the previous formula and the transition matrix. So obviously this would be a bit of work to calculate out manually, so I wrote a program to do it for you. It's hosted on GitHub, so you can see the link to it down below if you want to play around with it. Yeah. So let's put in, for relevant to this keyboard, 8 keys, and run the simulation. So first of all, it shows up our transition matrix here. You see zeros all the way across. And when I started seeing these, I was very surprised that I didn't realize earlier that we would have Pascal's triangle showing up here and upside down Pascal's triangle showing up here. Math and stuff everywhere connected that I don't realize until I stumble into it. It's great. So anyways, after that, it shows you your chord transition sequence from the 0 transition, as I showed you, down to transition 1. So let's get some more transitions. Transition 2, that's the number of chords that were on my original keyboard, where you had to press all of the keys and then release all of the keys, which was 255, enough to make a fully functional keyboard, as you can see, but not so many compared to if we had, say, a sequence that goes a little bit further. There we go. After 5 transitions, so that's like pressing a key, pressing a key, pressing a key, pressing a key, and releasing, we get up to my mega favorite number, 44,220,464. And yes, I selected that as the lowest number that was over 1 million from this sequence, which of course keeps going and gets very, very big quite quickly. But I think remembering a sequence of 12 chords so that you could have this many possible letters to put into your computer would start stretching the human hardware side of things. But I think it's quite interesting, and certainly should be possible to memorize sequences of chords with only 3 transitions in your sequence. You get 12,000 different inputs you could have, and then up to 700,000, and then of course my mega favorite, 44,220,464 possible sequences. Oh, thank you for watching. Hope you enjoyed. Go ahead and sync up your own mega favorite number if you don't already have one. Who doesn't already have a mega favorite number? It's quite a bit of fun.